Kia ora tātou, welcome back to this next session on analog to digital conversion and the analog to digital converter within the Atmel microcontroller. So what are we all learning all about? What is it all about? It's all about being responsive and reactive to real world events. And when I say real world events, I mean a lot of the real world is in analog form. It's not in digital form. That's why we've got to convert it to digital. So what we use is the ADC. And what I want to do is just pop back to the notes from Lecture11 101 from last year and just have a quick review. So really understanding the relationship between the real analog and the virtual, I suppose, digital world. So we need to be able to convert analog information to digital data and understand this word quantization. That's very important. And understand this concept of resolution. So let's have a look. What's quantization? Well, basically, we might have this continuously varying signal. We can call that a sine wave or a cosine wave if we want to, but it doesn't really matter. It's any continuously varying signal. And the reason I've done this is and shown it in this way is so that it makes it nice and easy to see the difference in levels. So say I had a 3-bit analog to digital converter. So that means that its input would go from, say, 0 to 10 volts. But its output would only be the numbers 0, 0, 0 through to 1, 1, 1. So that's from 0 to 7. So that's our 3-bit converter, which has 8 levels on the output. So that means that, say, for instance, at 5 volts, if we're just above 5 volts, let's call it 5.1 volts, what we've got here is our output will be 1, 0, 0. But notice also that at 5.2 volts, it will also be 1, 0, 0. And at 5.763 volts, it will be 100. In fact, at 6.249 volts, it will be 100. So this whole range quantizes into 100. So that's what quantization is. It's the process of mapping this continuously variable signal into a simple single binary step. Now, of course, once this reaches 6.25 volts, sorry, the output of the ADC will become 101, and it will stay that until it gets to just below 7.5 volts. And when it hits 7.5 volts, it will then become 110, and the output will stay that way until the voltage in reaches 8.75. So what we're saying here, or just below 8.75. So what we're saying here is that this ADC converter will convert between 0 and almost 10 volts. In fact, we will say that at 10 volts, 11 volts, 12 volts, it cannot go above 111. So it will limit that at that level. It will just cap it at that level of 111. Of course, that means that when you want to convert this signal back from its binary form into a nice analog form, you cannot get the same signal out. In fact, what you end up putting in is perhaps a nice signal in like this, perfect-ish sort of sine or cosine wave, and what you get out of it is a stepped waveform. And obviously, the more steps you have, the more likely this waveform is to approximate what's going in. And that again depends on the quality of your system, but really the quality of the environment that you're working within. What does it dictate? What do you need in terms of being able to resolve a signal into digital form? We're going to cover that sort of thing. So the thing to remember there is resolution. It's this single step size here, and this resolution is the analog and the amplitude divided by 2 to the power of number of bits. Okay, and so in this case we've got 10 over 2 to the power of 3, which equals 1.25 volts. Now, let's have a look at our notes for ComSys 201. So we've got this signal on the outside. Well, how do we get it into a digital form? Well, actually, the first thing we need to do is we need to turn whatever it is in the real world into a voltage. And typically, you know, the most fundamental aspect of that is using the voltage divider. And that is just absolutely crucial that you understand that this device is some sort of hardware equivalent fraction device. So the voltage across this resistor and the voltage across this resistor are the relationship of the values of the two resistors. And so what we normally do is we don't look at the resistance of the voltage across this resistor. What we look at is we look at the voltage across both resistors and compare it to the output. And in that case, what we have is a very simple relationship. We don't have a formula, we have a model. And what that does is it models for us the relationship between the input and output voltages. And that's based upon the relationship between the two resistor values. And so we get this equivalence type fraction operating here. We just don't normally talk about the voltage over one resistor compared to the other. Again, we just talk about the voltage over both resistors compared to the voltage over this resistor. And we end up with this simple model, very simple relationship. Now that's because our resistors at the sort of frequencies and signals we're looking at, they're linear devices, okay? There won't be anything complex about these, that's for sure. Now, what we're going to do then is we might know one of these values and another couple of the values, but we want to work out the other one. And this could be our unknown, would be V out, for instance. So V out, of course, is the R2, is this voltage here, times this voltage over the sum of the two voltages. And it's just a matter of manipulating this equation, this model for this. V in, we can do that. And I'm going to leave you to work out R1 and R2. Okay, they're slightly more complex. Okay, but it's worthwhile doing this exercise. Just because you know you can do this exercise doesn't mean to say you should avoid doing it. And so I really suggest that you do get on and just do these now and think about them. Get them out of you, get them written down somewhere so that you've got them in front of you when we're going through what's happening over the next part of this chapter. So what we're going to look at is, describe the significant characteristics of the internal ADC. So the internal ADC, what does that mean? Inside the microcontroller, what have we got? What we've got is an analog to digital converter. So let's just have a look on the left-hand side here. There's the analog to digital converter. If you click on the analog comparator by accident, hey, it's worthwhile having a look at this. We're not going to talk about it in the course, but I'll just bring it to your attention that there's actually an op-amp, little comparator type op-amp built into this device that you can use to compare things. And actually then you can get it to trigger interrupts when things happen. So this again is a sort of an analog, but it's not like an analog switch. If the voltage goes above a certain level, hey, send me an interrupt. Interesting, but not what I'm going to talk about now in any detail. So let's go to the analog to digital converter. Let's see, what do we got here? It's 10-bit resolution. That means that it can count from 0 up to 2 to the power of 10 minus 1. I'm just going to pause for a second while I cough. Okay, I'm back from my coughing now. Geez, let's go through this. So 10-bit resolution, it can go from 0 up to the power of 10 minus 1. We'll look at these numbers in a minute. It's not quite linear. It's pretty good. It's saying there's half of its least significant bit of linearity, okay? It's also not quite accurate, but it's plus or minus 2 of the least significant bits in terms of its accuracy. So yes, it's going to be pretty good, but sometimes you're going to have to figure out what are the limitations of this device, depending on what you're wanting to use it for. So we're not going to go into these in detail, but you need to know that actually it's not perfect, okay? These electronic circuits are not perfect. They work within a range. Now, it can take a certain period of time to do a conversion. It cannot do it in one cycle. We're going to go over this in detail, actually. That means that, of course, it can only do so many conversions per second. There are 6 multiplexed single-ended input channels. What does that mean? It means that you can plug in 6 different voltages to this analog to digital converter, and you can measure one at a time. Okay, you can't measure all 6 at the same time, because what it will do is it will switch from one to the other depending on when you want to do the reading, and each one will take a certain amount of time to be read. Okay, now there's also a couple more additional channels in certain chips. These are the types of chips that you're using, and we have this, excuse me, we have this chip on the Nano board, on the Explained Mini, and on the Arduino Uno. So that means that you've actually got another couple. So you've actually got 8 ADC inputs on these boards. It has an internal temperature sensor control. Okay, it has an optional left adjustment. Now we'll cover this in detail. The input voltage range must not exceed VCC. We're running our boards with the 80 megas on them of 5 volts. So you cannot exceed 5 volts. Do not exceed 5 volts. We have a reference which can be selectable to 1.1 volts, and I'll go into this in detail. It can operate in a couple of different modes. One of them is free running, which means it's continuously doing conversions. Or another one is you kick it off and it does a single conversion, and then you read the result, okay? And then there's also interrupt space, so that when it's done a conversion, it'll interrupt you and say, hey, I've finished my conversion, come back and give me some, give me a bit of space, and I will give you this value from the conversion. And it's got some sleep mode stuff. We don't go into sleep and getting the microcontroller to sleep in this course. That's something you can research on your own in the future if you need to use the sleep mode. Not hard to use. So we're going to look at quite a few of these in detail. Now, the particular type of ADC that's used in the Atmel AVR is a successive approximation one. And again, you know, we don't go into much detail about how these ADCs work. Now that you've got an understanding, or certainly by the end of this section of the course, you'll have a great understanding of ADCs, you can start thinking about, well, there are different ways of doing this, and some of them have different features. But in the AVR, we use a successive approximation one. We've got our analog multiplexer. Now remember, you've talked about digital multiplexers, so we're going to have a quick look at what an analog multiplexer is. And then there's also a sample and hold circuit, which means that because it takes a certain period of time to do a conversion, the ADC needs to have a stable voltage that it's reading. So what it does is it just switches the voltage that you're measuring onto a capacitor, holds it there while it does the reading, okay? That's what that means. It's got its own separate analog supply voltage pin, AVCC, and we'll look at this as well. And it's got, and your reference voltages are typically 1.1 volts, okay? Yeah, let's go into the notes and go through some of the detail on the notes, okay? Right. So now that we've had a quick squiz at the data sheet, and again, the reason I'm taking you to the data sheet is because you need to know it. You need to know your way around the data sheet. Okay, when it comes to, you know, answering questions in a test or an exam, you need to know your way around the data sheet, okay? It's completely critical. But the reason I'm doing that is not because I'm going to stick it in the exam. It's because an engineer lives and breathes inside data sheets, okay? Wading through pages and pages of information, trying to figure out how things are working together. It's what we do a lot, okay? So, yeah, I can't tell you the number of data sheets and books and technical journals I've looked through in my life to try and figure out things and solve problems, okay? Now, we've already talked a little bit about quantization. It's the process of mapping this continuously variable signal to a digital one, okay? And it replaces each real number with an approximation from a finite set of discrete values. What does that mean? Just exactly what I said back here in the other notes, okay? What that means is that this value here will be replaced with this digital approximation. That's what it's all about. So resolution. Now here, we're going to get into something just a little bit strange, okay? Resolution. Now, I've already told you that resolution is the voltage resolution, okay, of the steps. And we worked out what the voltage resolution is. It's the amplitude over the number of bits, okay? So what is this saying when it's saying resolution is the number of bits in the digital output code? Well, this is just how we say it in engineering, I'm afraid. Sometimes we mean the same thing, okay? And sometimes we use the same word to mean slightly different things. And that's what we've got here. So we can talk about the voltage resolution, which is the range of a single bit change in our ADC, or we can talk about the resolution as just simply the number of bits. So in our example here, in this example here, we were talking about 3 bits, okay? This has a resolution of 3 bits. It has a voltage resolution of 1.25 volts, right? Here, we have a 10-bit resolution. Okay, so I will tend to try and distinguish between resolution by saying resolution or voltage resolution, just to be clear about that. And of course, there are 1,024 discrete values, and they go from 0 to 1,023, which means there are 1,023 steps in the process. So just getting that clear in your own mind about, again, how do these numbers work? It starts at 0, finishes at 2 to the n, and what 2 to the n minus 1, and then what you've got is the number of steps in between, okay, is 2 to the n minus 1. So that means that there are 2 to the n discrete values, because you've got to include 0 in there. Now, when the input is 0, the analog to ADC output is 0, okay? And when it is equivalent to the reference voltage, so we're comparing this voltage against the reference voltage and creating some range of numbers from 0 to 1023, then when these two are equal, what you will get out of this is 1023, which of course in binary is, in binary is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it's a 10-bit number. And of course in hexadecimal, that is 0x3ff. Okay, so this is the range of our ADC output values, which of course means that these don't fit inside a byte, because a byte can only take up to 255 values. We've got an extra 2 bits on our number, so that means we must be working in 16-bit variables with this. Okay. Now this is just, again, a simple ratio. Of course, there are some minor accuracy and linearity issues which you might have to compensate for in some particular roles. We're not going to go into them here. Just you need to know that they exist. These things are not perfect. Okay, they work within a range of accuracy and non-linearity, which means basically that although this is a simple ratio, it's not exactly a straight line. Okay, there are some subtle issues in there, and we're not going to look at them in this course, but we're going to think of it as a straight line. It's good enough for what we're doing, and certainly the exercises in the simulator and the question tool I built are all based upon a straight line accuracy. So you don't have to worry too much about these errors. So that means that you can think about this simple ratio, and really it is really simple. It's the output value over our available range, which is 1023, and then that's divided by Vn over the V reference, and that's it really. And the only thing you need to know is what's Vref. Okay, so what is Vref? And in the ADC we have 3 different reference voltage options. Okay, so we can just jump back into the data sheet, and I'm going to expand this down, and I'm going to look at let's see, where would I find my little diagram describing how this thing works? Oh, here it is here. Oh, okay, so what we've got here is we've got, now this is the thing about a successive approximation ADC, is it actually has a DAC inside it. And so what it does is it converts the binary number to an analog voltage, compares that analog voltage to what is coming in, and then it does a bit of a counter thing here. So I'm not going to go into this, but this is why you're seeing here a DAC when we're actually talking about an ADC, is because this is the process of doing an analog to digital conversion using successive approximations, and just that's why it's there. Okay, so we need to compare it against an input voltage, and the input voltage we've got can be the internal voltage reference of 1.1 volts. Be wary, it's not exactly 1.1 volts, but you can calibrate this. Okay, you can put your own external reference voltage on this, or you can use the power supply for the analog to digital converter, and that's what AVCC is. So AVCC is usually, and pretty much always, connected in some sort of arrangement to VCC. So these 2 voltages will be the same. Okay, that would be most common, certainly not more than VCC. Now that means that this voltage here is 5 volts. So we could be doing our comparison against the 5 volts on the nano, or we can do it against the 1.1 volts, or we could plug in a separate reference voltage if we want to, and we could do a comparison against that. And you can simply see here that what's going on is that this multiplexer here is just choosing which one of these will be used. And these 2 bits in this register are how you decide what the analog reference is. Simple. Okay, so really, we're again looking at the data sheet. Let's go back to the notes. And before we wrap up, let's just have a look at this. So if I've got an analog to digital converter value, then really it's a matter simply of popping these values into the model. And what will come out will be the ADC value. Let's just say this is 0.67 volts over 1.1 because that's our reference voltage here. That's what I've decided to use as reference voltage. And of course it's times our range is, oops, not plus, but times 1023, which means that, you know, this will give us the number 623. Now let me just stick that on my calculator. And let's just do this on the calculator. So I'm in standard mode, 0.67 divided by 1.1 and times 1023 equals 623.1. Now, why am I not writing down 623.1? I'm working simply with digital logic circuits which aren't configured to have decimal places. Okay, we are working with whole numbers. Our registers work on whole numbers. We're not talking about how you might program your code to use a double or something like that. Okay, we're talking about whole numbers. This is just going into a register, so we cannot have a 0.3. Now, say for instance that the voltage I was using was a little bit higher, and this was 623.7. It would be truncated, okay, or math floor would be the appropriate thing there. So remember, what we're talking about here is actually it's not just a simple decimal calculation. We're only ever working with whole numbers and we're truncating them, okay? We lose that, we lose anything that might be a decimal place. It's just gone, it doesn't exist. And the reason that it doesn't exist, okay, is because really what we're looking at here is we don't get any of these in-between values, okay? It's either this whole binary number, or it's this whole binary number, or it's this whole binary number, okay? There are no in between parts. These are all integers, and that's it. So as you go up in voltage, it doesn't trigger to the next level until here. So that's what we're seeing here, is the fact that yes, 623 is the output of 0.67 volts, but also this represents a whole range of values. It's not exactly 0.67, it represents a range of values that will give us 623. Now, again, here we can look at the ADC value of this, which is, you know, 2.2. Let's just put this in my calculator, and we'll go. Now, I want you to think about this, because I'm just not plugging numbers into a calculator here. I'm going to go 2.2 divided by 5.03. Now, why did I say 5.03? What a weird number. Okay, well, the reason it's 5.03 is because your VCC voltage will fluctuate all over the place. Quite likely, okay, it won't be stable 5.00000 volts, okay, it might be 4.83, it might be 4.91 or 5.1. So you get all these sort of voltages. And of course, if that fluctuates, then what's coming out of your ADC can be quite unreliable. So, you know, that's why I've used these numbers here and just popping them. So 2.2, let's see, that's times 1023 equals 447.435. So what do we got? 447, okay? So that's over 5.03 times 1023 equals 447. So you can see, again, this 447 point whatever it was, it's gone, okay? Because all we're doing is we're finding out which one of those discrete values this voltage falls within. So that's really important to understand what's going on here. You can't look at this as some sort of formula. It's a model for how an analog to digital converter works in converting a continuous range of numbers to a discrete range of binary values, okay? So you can't just look at it as a formula. It is not. It is a model for a very specific device that will not actually work like a formula. So don't think of it like that, okay? So I'll leave you to work out these other two. What's the input voltage if we've got 754 coming in and a VCC of 5.07? You should be able to work those out without any difficulty and come up with something like 3.74 here. And I think about 0.465 volts I've got written here. Now, I'm going to stop at this point, and this is the first part of the lecture. So I hope this little introduction to the ADC is going to be beneficial to you. And what I really want to encourage you to do is get into the practorials and get into the assignment questions now on ADC, okay? Because they're going to help you really understand and grasp these issues. Cheers.